let's proceed on to the next chapter, in which we introduce really exciting day, a new force law, namely the magnetic force, and then associated with that is the magnetic field. So anytime you get a new force in physics, that's a red letter day, right? uh, I'm probably not going to tell you anything in regards to magnetic force and magnetic field in this introductory part that you don't already know or have seen someplace before. But it helps us to set the sign conventions and the notation that is used in relation to magnetic fields and gives you a little bit of historical background on it. As far as we know, the magnetic force was observed sometime in the 5th or maybe 6th century BC. The Greeks reported it in the 5th century, and they became aware that there were certain rocks, which are sometimes called lodestones, that could attract other lodestones as well as pieces of just regular iron ore. And these were first found, as reported by Thales, I believe, in Magnesia, which is nowadays present-day Turkey. Okay? And that's where we get the word magnet and magnetism for the phenomena. There's in terms of the historical context, this 6th to 5th century BC is somewhere about the transition from a Bronze Age into the Iron Age, and to smelt the iron takes some significant technology to just get temperatures high enough to melt the iron ore. But uh, once you find the uh, once uh, uh, once you're able to do that, then you can create metal and steel swords and spears and plows and that sort of thing, which are much more rugged and durable, much stronger than what had been used previously for these, namely bronze, which is a mixture of copper and tin. And the Trojan War, for instance, was fought with the bronze implements, so that was before the Iron Age. In any event, apparently the first iron, once people developed this technology to get hot enough flames to smelt iron, some of the first mines in which they mined iron ore were in Magnesia, and then occasionally, not all the time, but they would find pieces of iron ore, essentially these lodestones, that would exhibit these attractive phenomena, both with themselves and with just regular pieces of iron. In about 1100 AD, so now we're progressed quite a time. The Chinese had developed what we would now know as a magnetic compass, uh, but it seemed to have just been a novelty item for them. There's no reported use that they used it for navigation, which obviously magnetic compasses have lots of good uses to knowing which direction is north and keep yourself oriented as you go in different directions. So for seafaring and that sort of thing. But what they did was they floated on a piece of wood in water one of these magnets, what we call a magnet now. And what they observed is that one end of it would always float around, since this would be free to rotate. Uh, it would rotate around so that it always went to the geographical north. And so if you mark one end of it, I just put a dot on one of these pieces of lodestone, or magnets we'd call it, and they would see that give it some time, set it any orientation you wanted, but eventually it would rotate so it lined up with north and south. And so it's a good instrument to determine what the direction of north is. This would be the geometrical north and the geometrical south. The end that rotated, in this case marked with a dot, was called the north end of the magnet, because it was the northernmost, and the other end was the south end of the magnet, which was the southernmost. So pretty pretty straightforward. Nowadays, we generally have things that I'll denote like this. Usually compasses I'll denote as an arrow, and this is a little magnetic compass. The arrow end is always the north end, and the other end is the south end. And then again, these magnetic compasses will rotate around so that they align with the geographical north-south direction, with the north end pointing toward the north. Well, in Marco Polo's exploits in China, he brings this technology back, and then people pretty rapidly developed it. Since he was a big traveler, developed it to help orient themselves with respect to directions. So we get the magnetic compass. In the 1300s, there was a series of experiments that was done by a variety of individuals, but they basically gave things that I'm sure you've seen before. They would mark the north ends and south ends of these magnets with that convention that arose from the magnetic compass. And you would find that if you brought two north ends together, they would repel. If you brought two south ends together, they would repel each other. These are repulsive forces. But if you got a south and a north end, they would attract. And that either end of the magnet, the north or south, would attract iron ore. Yeah. So here's a magnet, regular iron ore, unmagnetized iron ore, and it would be attracted to either a north end or a south end. So it was sort of reminiscent of electric charge, but a totally different force, and apparently unrelated to electric charge, at least at this early stage. One thing that's a little bit different with magnets is that we never see, it's like positive and negative charges. So like poles repel and unlike poles attract. It's like charges repel and unlike charges attract. So it's similar in that regard. With a major exception is that we've never observed an isolated north pole or a south pole, so all by itself. Unlike charges, which we observe lots of ions that have positive charge and negative charged particles as well. So we do see isolated electric charges, but never isolated magnetic poles. What in fact is found is that they only occur in pairs, north-south pairs. And you can try these experiments. People did them over and over again. They, well, if I've got a north pole here and a south pole here, I could just saw this thing in half, and then I'd have a north piece of iron that had only north pole and only south pole on the other one. But in fact, what happens when you do that they spontaneously, this one that was the north, it would spontaneously arise a south pole here, and the one that would have been south would spontaneously arise a north pole on this side. Uh, so for magnets, the poles only come in north and south pairs, and no one has yet, anyway, observed an isolated magnetic pole, which sometimes is called a monopole or a magnetic monopole. And occasionally you see experiments in which they try to see if they can detect these, but through all the looking, they've never been able to find an isolated magnetic pole. In the 1500s, William Gilbert in fact, wrote one of the first treatises, the first books on magnetic and magnetism, magnets and magnetism. William Gilbert was a a physician, and I guess he attended the royalty, and I guess he didn't have all that many patients, so he had a lot of spare time which he investigated magnets. But what he did and developed, and maybe is the idea that the Earth, in some respects, behaves like a giant magnet. Uh, Magnets are really sometimes they're represented, or these compasses, I should say, with a little diamond shape. The black end is usually the north end. If here's one that has a little arrow, they magnetize. It's a little magnet with the north end, the arrow end, and it's free to rotate about a pivot point. And then what I'll represent these is, if I'm looking at a compass, just these with a little north and south end. Sometimes I'll drop the circle around it. So, but uh, his explanation, which is essentially right, is that the Earth has to be what causes these compasses to orient themselves so they point north. You know? And his summation was, well, there had to be a big south pole to our geographical north that would attract the north end and repel the south end. And since they always come in pairs, the North Pole was at the south, geographical south of us. So, and that is essentially right. Here's the Earth, and the Earth's south magnetic pole is the one that is geographically to our north. In 1819, and if you look at 1819, that's getting at the time of Faraday, who had proposed the electric field concept. And Hans Ørsted, who was a Danish physicist, discovered around that same time that electric currents, moving electric charges, produce a magnetic field. And we'll talk about that in more detail a little later. But the field concept by Faraday carries over into the case of magnetism. And in fact, it's very easily seen. You've probably seen these where you distribute iron filings around a magnet, a bar magnet in this case, and it'll display patterns that look something like this. Even if you don't have that, I can take little magnetic compasses and move them along, and they will always point in the direction of the magnetic field. And since the point end of this compass is a north pole, it gets repelled by this north pole, but it's along the lines that the iron filings would fall. So the hypothesis, in fact, is that, well, you have surrounding any magnet is surrounded a conveyor of the magnetic force on these little compass needles that carries or conveys the magnetic force. And that's usually given the symbol B, and is either called the magnetic field, or sometimes you'll see it called the magnetic induction. Some books at upper levels, they'll call it the magnetic flux density as well. But we'll carry on with this field concept as a magnetic field in much the same way as electric field. Have field lines that display the magnetic field. The field lines will be very dense where the magnetic field is strong, and they'll be spread out where the magnetic field is weak. And magnets are the strongest right at the two ends, and so that's where all these magnetic field lines converge, and they'll get a high density there. Just to give you a prelude, Ørsted actually ran a current, and he discovered, and we'll talk about this experiment in more detail a little later, but he discovered that moving charges, currents, produce a magnetic field that circles the wire in this fashion. So if I look down on this front end of it, so the current's coming right out at me, the magnetic field lines circle around it in this fashion. And magnetic fields that are produced by currents are generally called electromagnets, and so the magnetic field exhibits this magnetic phenomena. Well, lots of experiments put together, and they found that through the late 1890s that the force on a moving charge was given by this V cross B expression. The Q can be positive or negative. V is the velocity of the charge Q, and B is the external magnetic field. And the cross is the vector product or the cross product between those two vectors. And we'll look at that in more detail in the next